I'm Jenny Grosslight from Agilent Technologies, here to describe and demonstrate how bus-level signal integrity insight can save you time by revolutionizing how you debug and validate your memory systems. Signal integrity begins with the design phase, where simulation tools help designers create the best designs. High bandwidth scopes are the definitive tool for making signal integrity measurements on the systems once the designs are fabricated and system turn on and debug begins. There has been a measurement gap in that a scope has 4 inputs. See all of the signals, all of the eyes relative to each other. Now, DDR memory designers can obtain qualitative bus-level signal integrity insight by comparing eye scans from the U4154A logic analyzer from all the signals in the system being scanned relative to each other and relative to the clock of the system to gain insight at the bus level. This qualitative insight does not replace the scope. It enhances the use of the tools to get to the root cause of their issues faster. Let's look at examples. 2 bus-level signal integrity views are available on the U4154A system. The overlay mode is the most popular mode for bus-level signal integrity insight. It is also the mode that is required to be able to set state mode sampling position. The next mode is a burst scan mode, also referred to as signal trace mode. In this mode, unique qualified scan views are possible. Several examples would be simultaneous views of all DQS and specific bubble scans, which are described and shown in the burst scan video. Let's go through the bus level signal integrity insight from the overlay mode. This is the mode where we're setting our sampling positions in state mode. It's also giving us a beautiful display of all of the signals relative to each other. In this mode, the clock-delayed copies of the DDR bursts of all signals are placed on top of each other so that the tri-state time of the data overlaps until we get one clear eye representing all 4 or 8 samples in a burst where we're going to sample the data. This also provides a view where we can see the signals relative to each other and gain signal integrity insight. Next, we're going to move to the logic analyzer to show the first example of the overlay mode signal integrity insight. In this first example, the issue was that a DDR3 DIMM didn't operate at the maximum speed. Bus-level signal integrity insight quickly shows the issue is with the read DQS2 on the DIMM, allowing for resolution of the issue. Opening up the iScan window and scrolling through the qualified scans of only valid read traffic, we see now each of the data bits relative to each other. As we scroll through the traces, we see all of the bits in a byte lane. At data 7 and data 8, we see the byte lane shift from byte lane 0 to byte lane 1. Again, the signals are pretty well evenly the same size. We see one bit with a little smaller eye. And as we get down, though, into byte lane 2, which starts at bit 16, where we see another shift over to the right for the whole byte lane, we start to notice that all of the eyes are smaller relative to the neighboring eyes. So looking at byte lane 2 and realizing that the eyes are smaller relative to the other byte lanes, we begin to wonder if byte lane 2 has an issue. Byte lanes are driven from strobes, so we can go look at the strobes relative to each other and quickly realize by looking at the eyes that DQS2 has a much smaller strobe eye. The strobes are driving the data. The problem is with DQS2 as a read strobe, which is coming off of the DIMM and going to the memory controller. I have had signal integrity gurus at different companies look at this example, ask them if they see the value, and they go, of course I do. Out of hundreds of signals in my system, I now see that I have a problem on the read strobe off the DIMM, and that is where I'm going to go with my scope to resolve the root cause of that signal integrity problem. In summary, when we look at the example of the strobe eye circled at the bottom, where DQS2 was smaller than the strobes on the same DIMM, and then compare it to where the DIMM manufacturer had corrected their issue with DQS2 on another DIMM, now we see that on DIMMs that can operate at higher data rates, there are open strobe eyes on all of the strobes and no closure of any single strobe. Many designers are working very hard to have their systems operate at lower voltages. For our example, we took a system and operated it at DDR3 1333, and we operated it at 1.6 volts, and then we lowered the voltage to 1.2 volts and compared the scans. This is a single signal example on the slide, but it is representative of what we saw across all address and command signals. And that is that we noticed the fall time at 1.2 volts on all address and command bits was sluggish compared to the fall time at 1.6 volts. This identifies an area of weakness that needs to be resolved for this system to be able to operate at higher data rates and lower voltages. Another example of the overlay mode, 1.6 volt versus 1.2 volt operation, was on the read data. The eyes are much wider for the same data rate at 1.6 volts than they are at 1.2 volts. This is also showing where rise and fall time became more sluggish when the voltage was decreased. Now, in an instant, in being able to view the signals relative to each other, the designers are able to say, oh, I need to work on the drive strength or the termination so that my rise and fall time will be sharper. Now that we've completed the overlay mode, now we'll look at the second bus-level signal integrity view, and that is the burst scan mode, also known as the signal trace mode. Here we'll look at a unique scan providing simultaneous views of all of the DQS in a system. To do the burst scan, we're going to overlay the copies of the burst, either a burst of 4 or 8, shown here as a burst of 8, and each time we overlay each sample on top of itself. So instead of overlaying all of the samples into one composite, we now see them fanned out, more like a scope would show us. Become concerned that here you're viewing the effects of the logic analyzer probe and the location, which might be mid-bus for convenience, and seeing all of the effects in the signal integrity result. And that's true. This is not replacing the scope, but it's enhancing the scope, because now we can make specialized scans, simultaneous scans, gain quick, rapid insight, and then know where to go with the scope and why, and do so quicker. So in this next demo, we'll look with the logic analyzer at an issue that is a great concern. To see all of the DQS, the strobes, relative to each other in one view. Unfortunately, scopes have 4 inputs. So here we're going to use bus-level signal integrity insight to show all 8 strobes in the system qualified where there were no back-to-back bursts and they were only read bursts. All 8 strobes are shown in one view, and we can scroll through the strobes. On the left, we see the tri-state, then a dip where the strobe goes into its preamble, and then each edge of the strobe is going to clock data in our system. Typically, the bursts are bursts of 8, so we see 8 edges of the strobe. Engineers can view the strobes all relative to each other, comparing them to see if they have similar preambles, similar signal swing, and if the signals are behaving as they expect relative to the clock. The clock will be at time 0. So we scroll through all of the strobes and have an excellent view of the behavior, and the tendency for them to go over to the right is the flyby routing. And here we go through all 8 strobes and have easy comparison. To obtain signal integrity insight, the typical U4154 configuration is shown on this slide. Thank you for watching. For more tips on how to make better memory measurements, please go to the websites listed on this slide.